With everybody. Let me get the chat thing going. Okay, hi everybody, welcome back. So we're going to do a little calculus today for a change. So let's see, a little administration. You probably already know there's a exam on Tuesday. I decided, even though I usually do 13.4 and 13.5 out of order, because I include them both on the same exam usually, and 13.5 is really needed to understand 13.4. I don't know why they're in the order they're in. I realized that it really makes sense to have 13.4 on this exam since I can't have them both. So what that means is we're going to talk about 13.4 a little bit just in sort of a functional way. How do you use Green's theorem? And then the actual meaning of why Green's theorem makes sense, that'll wait until after we talk about 13.5. It's a little bit weird, but it's good to put all the line integral things together. So that's the way we're going to do it. Don't forget there's practice, fun packs, and so on the course website. And I'm ready to get started unless anyone has a question. Does anyone want to say anything or just?
Yeah, the last time you talked about the exam, you mentioned we were going to talk about 13.5. So there's no longer 13.5 on the exam, correct? That's
right. I could only do one extra section besides after 13.3. And I realized it didn't really make sense to have 13.4 on the next exam. So I made that change. Yeah. Anything else?
I just have a quick question.
Sure.
I don't want to spend too much time on it, but has the administration told you anything about the fall semester specifically yet or not?
Nothing at all has been decided. And there's like 5 different models being thrown about as possibilities, ranging from things as like having half students attend every other day of the week, or having the session split into 3 5-week sessions where you take just shortened classes for longer periods, or having it all offline, or having us start and then go home after Thanksgiving. Or I mean, there's a whole variety of things being talked about, and no decisions have been made as far as I know.
Okay, so, thank you.
Yeah, we're all pretty much in the dark. The uncomfortable thing is the university has to make a decision before they really have enough information to make a good decision, and obviously they care very much about people's safety, and so I really don't know how that's going to pan out. As soon as I get any inside information, though, I promise that I'll let everybody know. I want to know as much as you do, absolutely. Anything else? Okay, so last time we were talking about something very important, and we know it's very important because it's called the fundamental theorem for line integrals. We have a little bit more to say about that, so let's go back into this section. Okay, I need to give you some definitions of things. And 2 of the definitions we're going to use right away. One of the definitions we're not going to use for a while, but let's just put them all together because they're topological ideas, and it's good to sort of, while our brains are still in this direction, just put them all in. Okay, so a simple curve, we all know what a curve is now, but a simple curve is a curve that doesn't intersect itself. So for example, this thing is, no matter how weird it looks, this thing is simple. And this thing is not simple, according to this definition of what a simple curve is. Another definition I want us to know is a closed curve is one where the endpoints meet. So it closes up. So here, this thing is a closed curve, and this thing is not closed. And actually, a lot of our theorems, just like in, well, I guess it's not that much of a parallel, but you know, back when you were in learning about calculus, I don't know where you probably talked about this in Calc 1, there were a lot of theorems that were like, if you have a continuous function on a closed interval, then blah, is sort of standard conditions. Standard conditions we're going to have for a lot of our theorems are going to be, we have a simple closed curve, both of those things together. So no self-intersections, and it starts and ends at the same place. Okay. One last piece of data of definitions I want to give you is not about curves, but it's about regions. So, so a region is called simply connected. So like a two-dimensional region, let's say. Well, let's see. There's, if it was just a two-dimensional region, I could just say if it doesn't have any holes in it. But simply connected has a meaning no matter what dimension you're in. And then saying it doesn't have holes doesn't really generalize. So I'll just say what the general thing is, and then I'll tell you specifically for 2 dimensions. Okay? So a region is simply connected if every single curve you can draw in that region can be pulled down to a point without exiting that region. I'm going to write that down, then I'm going to draw a picture of what I mean. Every single closed curve in the region can be pulled down. Now, this is the vague part. It's not vague in mathematics. I can define it very carefully as a topologist, but the definition will take us too far afield. So that's why I'm going to keep it vague here, is pulled down to a single point without having to exit the region. Okay, so here's an example of a simply connected region. So here I'm thinking of the region as being the 2D region inside, right? Not the boundary. In these pictures, I was talking about the curve itself, but here I'm talking about the region inside the curve. Okay. So this region, any curve I can think of, you know, here's a closed curve, and then here's another closed curve. Oops, I didn't mean this to have it. Looks like it has a tail on it. I didn't really want that to happen. Let me try that again. Here's another closed curve. The point is, so when I say that it can be pulled down to a point, imagine that that the curve actually lives in there and I'm allowed to drag it along through the space. So I can drag all, let's say I just drag all the points this direction, all towards, you know, the starting and ending point. So I can pull it all down to the point, and I'm always staying inside the region. There's no problem. So this picture that I've drawn for you, this region is simply connected. Oops.
Why does that matter to us?
Because some theorems are only going to be true if conditions happen on simply connected regions. So we're trying to understand what the hypotheses might mean. That's a really good question. And actually, there's an important theorem. Well, there's a reasonably important theorem that we're not going to get into as much as I usually like to get into it because we're on an abbreviated time, but for which this is important. And if you don't have simply connected, then the statement's just really not true. So we might as well know what it means when I tell you what the theorem is. So this is simply connected, and just for you know, thoroughness, here's an example of something that's not simply connected. So what I'm talking about here, when I draw these two circles, curves, I'm not talking about the curves themselves, I'm talking about the region in between the two curves. So in other words, I'm thinking that this part in here doesn't belong to the region. Does that make sense? Okay, so in this case, some curves can still be, some closed curves can still be pulled down to points. This one's okay, but any curve that does this, that goes around that hole, cannot be pulled down to a point. Or it can be, but if it does, it has to exit the region, right? It'll have to cross through this region in order to get down to a point. Okay. Cannot be pulled down to a point.
And this applies to third dimensions as well. So like if you had a torus, would that work too? Where
Yes.
it's a simply connected region?
Exactly. So a torus is not simply connected. If you were on the surface of a donut, you can imagine like cruising around the top of the donut, and then that curve, maybe you could make it smaller by going like further into the middle, but you couldn't pull it all the way closed and stay in the donut. That's exactly right. And but the sphere is simply connected. So if you have like an equator, imagine you could sort of slide that around the top and have it sucked down to nothing. Okay, so exactly right. So so let me just say in 2D regions, you can equate this idea with not having any holes. So these were 2D regions. And if you look right here, this one didn't have any holes. It was all filled in. This one had a hole right here, and that's what caused the problem. If I was in 3 dimensions, if I had all of 3 space and I had a hole, like let's say the origin was missing, that wouldn't matter, right? I could just pull a curve around the origin doesn't matter. But if there was a whole axis missing and I had a curve around the axis, then that would be a thing that would get in the way from putting it down to a point. Okay, that's more than I need to say about simply connected. These are just some definitions, and we'll get back to them in a second. In fact, we're going to get some of it right now. So this is a very important theorem called the equivalence theorem. And the equivalent says the following are equivalent for a continuous vector field F. Okay, what do I mean? So I'm going to give you a list of 4 things that might or might not be true about a given vector field. To say that they're equivalent, what that means is if one of those things happens to be true about the vector field, then all 4 of the things will be true about the vector field. Or if one of those things happens to be false about the vector field, all 4 of the statements will be false about the vector field. Okay, so that's what I mean by saying they're equivalent. Okay, I'm not saying that this has to be true. I'm saying if one is true, then they're all true. So one of the conditions that may or may not be true about a vector field is that F is conservative. F is a conservative vector field. That's one condition. So that's equivalent to, for every simple closed curve, the line integral around C Wow, let's think about this. Maybe we can figure out what this is. So can we use the fundamental theorem of line integrals? What's the condition for using the fundamental theorem of line integrals?
The vector field must be conservative, and
Vector field must be conservative.
And the function f must be a potential function for the vector field.
Yeah, that's right. Good. So the vector field has to be conservative, and then we also need a little f, which is a potential function. Okay. If we're thinking if the case where f is conservative, what would be equivalent to that? Well, then I can apply the fundamental theorem of line integrals to this. I don't know what the potential function is, but if it's conservative, I know there is one. I just don't happen to know what it is right now. But given that there is one, I know that this line integral is that potential function at one endpoint minus the potential function at the other endpoint. What do you know about both endpoints of a closed curve?
They're the same.
They're the same. So what do you think the value of little f, I don't know what little f is, but what do you think the value of f little f at one endpoint minus the value of little f at the other endpoint has to be?
0.
Has to be 0. Okay, so we've just proven in our minds part of the equivalence theorem, which says if you have a conservative vector field, then the fundamental theorem of line integrals guarantees you that the line integral around that curve is 0. Think how much time that could save you. If you know it's conservative, you don't even have to do the line integral. You can just say, hey man, that's closed curve at 0. Okay, so that's another thing. But also it turns out that it could go the other way. If for every simple closed curve, the line integral is 0, then you know it's conservative. That's impossible direction to, well, you can't really go that direction because you can't prove something about every simple closed curve, but in any case, it's true. Here's another condition equivalent to those two conditions. For any two oriented curves, C1 and C2, that have the same endpoints, so and we should be thinking, in our minds, we should be thinking, you know, here's C1, and then maybe here's C2. You have the same beginning point, same ending point, but they're different curves maybe. What do you think is true about the line integral? How do those line integrals compare?
They're equal
Yeah, they have to be the same. Why would that be?
because it only depends on the starting point and ending point.
Exactly. It only depends on the starting point and ending point. If we're in the condition where we've got the conservative vector field, then we can use the fundamental theorem of line integrals. And that says that the answer is only going to depend on the starting and the ending. And since they have the same starting and the same ending, we're going to have the same value for the line integral. This can be useful. I mean, one thing that you could do, let's suppose you knew the vector field was conservative some other way, but you were unable to come up with a potential function for some reason or another. And also you weren't able to figure out this line integral. You just couldn't do the computation. But if you replace this curve with some straight line or something like that, suddenly the computation's easy. You can replace it. You can throw this curve, you can throw this curve away and replace it with any other curve with the same endpoints and do that line integral instead. And maybe that's a way to simplify your work. Okay, and then the last condition, well, is obvious because it's part of the definition of conservative, but let's just include it. F is the gradient of some potential function, little f. Okay, so that's the equivalence theorem. And we may end up using that in some of our calculations. I could ask you to do a calculation, you would say, oh, I know it's conservative, so and I know this is a simple closed curve, so by the equivalence theorem, the line integral around the curve is 0. And then that just saves you from doing the whole computation. But you need to tell me, remember, the name of the theorem and what the conditions are. And the condition would be, I know that I have conservative vector field and a simple closed curve. Okay, so this is an important theorem. And what questions do you have about this theorem before I show you some vector fields? Nope. Okay, let's look at some vector fields. So these are the vector fields I had from class before. And
Professor, I'm sorry, I had a quick question before
Sure.
you. The examples that you gave us just now, if we could go back to that, I'm sorry.
Sure.
Are C1 and C2 closed, or would those be considered open if they weren't touching each other? Because wouldn't C1 and C2 technically have to have the same endpoints to be closed?
Yeah, and C1 and C2 don't have to be closed.
Okay.
That's not a condition. That's a condition for part 2 here.
Okay.
A closed curve to get 0. But here could be any two curves. They might not have the same starting point as they do at any point. But
So,
they share a common starting and share a common ending.
yeah, for instance, if you were to have, for the equivalence theory on part 2, if you were to have like two circles or two parameterized circles that are different curves touch at one certain point, that would be an okay time to like apply the equivalence theorem for number
Yeah,
2.
or you just really need one circle. For part 2, you only need one closed curve.
Oh, okay, gotcha.
Yeah, for part 2, you need 2. And actually, let's think about, there's kind of a relationship between these two, because see, if I look at this equation, I could move one to the other side and get 0, right? Integral around 1 minus integral around the other is 0. Well, that's the same thing that I get if I integrate forward along C1 and then backwards along C2. Remember, integrating in the reverse direction, opposite the given orientation, is going to give you a negative sign. So doing this and this is going to give me a 0 line integral because of 2, and also 3 supports that with this picture too. Okay, let's look at the vector fields. Okay, so this is a vector field from last time, perfectly tame vector field. Is this vector field conservative? When I'm in class, when I have a whiteboard, I usually can have the statement of the theorem and the vector field up at the same time. We don't have that luxury, but you've got the theorem, I hope, in your notes. So can you look at your notes and tell me whether this vector field is conservative? You don't even need to know what the formula is to decide this question. Only the picture. Think about condition 2. Is the line integral around every simple closed curve, is that line integral going to be 0?
Yeah.
Yeah, okay. What about this closed curve? What if I do this? Is the line integral around this closed curve equal to 0?
Yeah.
Actually, it's not. What does the line integral measure?
Oh, is that because it's the tangent to the curve and the vector field?
Yeah, that's right. How well does the tangents to the curve line up with a vector field? And these aren't perpendicular. They're pointing in roughly the same direction. I didn't make a very good circle, so they don't exactly match, but they're pointing in roughly the same direction. So we're going to be picking up positive values of the dot product all the way around. We're just going to add a bunch of positive values to the dot product. So the line integral around this curve with this orientation is positive, not 0. So this is, yeah, say that one.
So what's different about this vector field and the continuous vector field? Like what's different?
Oh, it is continuous, but it's not conservative.
Oh, okay.
Yeah. So this one is not conservative.
Can we see the vector field equation?
Sure. Yeah, and so if you try to do that, let's see. So this should have been a capital F. My notes are a little bit old, and we had different notation in a different class I taught. But so if I wanted to find a potential function, I would need this property. I would need some potential function. Little f sub x would have to be y, and little f sub y would have to be negative x. Remember doing these yesterday or whatever? Well, if little f sub y, that would mean that f would have to be x, y, plus any old function involving y. And this thing would say f is negative xy plus any old function involving x. And those aren't compatible. I can't find a function that does both of those at the same time. So that's another reason why not conservative. But I didn't even need to look at the formula. Just right here, I thought up a curve for which the line integral isn't, a closed curve for which the line integral isn't 0. That's enough to give it not conservative by 4. By property 2, I don't know why I said 4. Does anyone have a question about that? Okay, what about this one?
wouldn't it be conservative?
Why do you say that?
Because if you were to hypothetically say draw a circle around the vector field, you would notice that the tangential lines would be perpendicular to the vector field lines at all the points on the curve. So
For
then you
all
could,
circles?
for a general circle, like for instance, like if you were to like have a unit circle parameterized.
Okay, let's try the, I'm gonna do a two circle because the unit circle, the vectors are too small. But if I did this circle, a radius 2, okay, I agree that for this circle, it seems like if I have to orient it, that the tangent vectors to the curve are always perpendicular to the vectors from the vector field. So I agree that, so let's call this C1. The line integral around C1 appears to be 0. I totally agree with it. But what about this curve? This curve is totally agreeing with the vectors for a while. And then it is kind of in opposition to the vectors for a while. If I know that there's a simple closed curve for which the line integral is 0, does that guarantee that the vector field's conservative?
No.
Exactly. Can you say why not?
Well, the equivalence theorem says that for every closed curve.
Good. That's exactly right. The equivalence theorem says if for every closed curve, the line integral around it 0, then you have conservative. Here, just because you have an example of a closed curve, okay, that's, you know, encouraging, but you would have to show that it worked for every single closed curve. And that's not really practical, right? There's how many closed curves are there? There's infinitely many. We just couldn't do it that way. So it appears, I'll just say, appears conservative, but we can't use the equivalence theorem. What we'd have to do is try to find a function whose antiderivative is there. And that's easy enough to do. If I had 1/2 x squared plus 1/2 y squared, then its gradient would be capital F. Okay, so it is conservative. But we don't know that for sure just because we can see a bunch of curves, closed curves, whose line integrals are obviously 0. That's not quite enough information. This conservative or no? What does it appear?
It appears conservative, I think.
Yeah, for the same reason as the other one. We don't really know for sure because there's too many to look possible to look at, but at least we can tell that the ones around the origin will have a line integral of 0. And looking at this, we can write the formula for that. What about this one? Conservative or not conservative?
Conservative.
Why do you say that, Juan?
I mean, just looking at the origin and those first like 4 points around it, the top left and the bottom right seem to counteract each other, and the top right and the bottom left seem to counteract each other.
Okay, so yeah, this seems to be going in the opposite direction of this, and this seems to be going in the opposite direction of this. Absolutely. Let's think about line integrals. Are there any closed curves around which the line integral seems to not be 0?
If you had a unit circle, it seems like it wouldn't be 0 because
Yeah, good. I'm going to make it a little bit bigger than unit because the vectors are so tiny, but it's exactly the right idea. If I have a circle like this, then the tangent vectors are going like this, and the vectors from the vector field are going like that. And although they're not in total agreement, they're still going to pick up a non-zero, a positive line integral, a positive dot product. And that's true all the way around the curve. So you're going to get a positive line integral. So the integral around C1 of f dr is going to be bigger than 0, so not conservative.
could you use arbitrary curves and arbitrary like endpoints to determine whether or not like a vector field is conservative?
You can use it to determine that it's not,
Okay.
but you can't use it to determine that it is. Because if you happen to get a 0, just like Delaney was saying earlier, if you happen to get a 0 for around a particular curve, that doesn't mean that you're definitely going to get 0 around every single curve anyone could ever think of. And that's what's required to show that it is conservative. Okay. Okay, well, what is it about, what can you see? This is a little bit of foreshadowing, I guess, but what do you see about this vector field that wasn't conservative? These ones are, this one's not. What was it about the ones that weren't that, that allowed us to exploit something to violate this 0 line integral business? Should I
They
ask,
were-
oh, do you have an idea, Delaney?
The ones that weren't conservative are like spiraling.
Good, that's exactly right. The ones that aren't conservative have some spiraling in it, have some rotating. And what we did was we put a curve right around where that rotation was, a closed circle, and then that was gonna pick up some positive values for dot products all the way around. Here we put a circle around where it's spiraling, we pick up positive dot product. Here there was no spiraling, no spiraling. There's some spiraling, we were able to, sorry, it's scrolling slower. Here there's some spiraling, so we're able to pick up some positive dot product. Okay, that's actually kind of the key. We'll find out in 13.5 that there's a huge connection between conservativeness and whether there's rotation or not. Okay, so that's what being conservative looks like. And I did that. So here's another theorem. The theorem with no name. It says, so if I have a vector field, and let's just call the components P and Q. So the first component function is P, the second component function is Q. If it is conservative, then, well, I guess I have to say a little bit more. If it's conservative vector field, and P and Q have continuous partials in a region, then cross partials are equal. So dp dy, the first component with respect to the second variable is equal to the partial of the second component with respect to the first variable. This actually, it seems pretty cool, except it shouldn't be surprising at all when you think of what does it mean to be conservative. If I think about what it means to be conservative, I'm not going to write this proof down because we're sort of short on time this semester, but if you think about what it means to be conservative, that means that that this function, this vector field came from some little f. So this thing was some little f sub x, and this thing was some little f sub y. If it's conservative, right, there was a potential function, and each of those components are the partial derivatives of that potential function. So if I take partial of p with respect to y, then what I'm doing is I'm taking partial of this component with respect to y. I'm doing f sub x sub y. If I take partial of q with respect to x, I'm taking little f sub y sub x. So the fact that these are equal, why is that?
That rule thing.
That rule thing, yeah. So it was a Clause's theorem or whatever, saying that the cross partials are equal, fxy equals fyx. Okay, so if you understand what it means to be conservative and as being the gradient of some real valued function, then this just follows from Clause's theorem. But it's true. Okay, so it's good to know. And so here's a question. Does this mean that if these cross things are equal, dp dy equals dq dx, then f is conservative?
What does the bottom line of the theorem say?
The bottom line of the theorem. You mean this right here? Or this right here?
No, up on the top, right above the dpdy.
Here, oh, continuous partials? Okay. Oh, CTS is a short, maybe, okay. CTS is a common shorthand for continuous. Partials. So if the partial derivatives exist and are continuous on some region. Yeah.
Thank you.
Okay, what do we think about this question?
Well, isn't it missing exactly what was just asked, where like it doesn't
Okay.
specify anything about continuous partials?
That's a good point, Joe. I didn't say anything about continuous partials. What if I do have continuous partials? Is that what the theorem is saying?
No,
No, why not? What's still wrong?
because the theorem saying like if A is true then B, and you can't then say if B is true then A. It's not like commutative like that.
Yeah, exactly right. Okay, it just says the implication goes one direction. It doesn't say it goes the other direction. Okay, a lot of times people will make that mistake. So I just wanted to be sure that we were careful about it. But there is a similar. But there are two things that one thing that's related and one thing that we can conclude from this. So the answer is no. This is called the converse. Of the theorem. And it's not necessarily true. The converse, making the if B then A out of an if A then B, the converse doesn't have to be true just because the original statement's true, which doesn't need to be true. But does it say that if partial P with respect to Y is not equal to partial Q with respect to X, then F is not conservative?
Could you say that the first question, the reason behind why the converse isn't true is because if you were to anti-differentiate with respect to the partials, you wouldn't possibly have a function or like a smaller function f that is equal to the gradient vector of the vector field?
Yeah, that's right. I'm not saying that the statement is always false. I'm just saying that right here, we can't assume this is always true just because we saw this theorem. This theorem isn't telling us that this has to be true. And in fact, you're right. It is possible that this could happen, and yet there is no little f. So yeah, that's what could go bad. And then what about for this question? So does it mean that if the I just call them cross questions, but if dp dy is not equal to dq dx, does that mean that that it's not conservative?
I would say yes.
Yeah, can you explain why, Adrian?
Because the theorem says that if your partials are continuous in that region, and that f is conservative, then they will be equal.
Yeah, so it says if it's conservative, then they will be equal. They're not equal, so it couldn't possibly be conservative because if it was conservative, they would be equal. So since they're not equal, then f can't be conservative. So yes, it does say that. So you can use this theorem to show that a vector field is not conservative, but you can't quite use it to show that it's conservative. But there is a related theorem. So moral. can use this to show F not conservative, cannot use this to show F is conservative. Okay, that's fine. We can still do something with it. Well, there's a related theorem, super related, which you can show it's conservative, and that's doesn't really have a name, but it's Theorem 6 in your book. So I'm just going to call him Theorem 6 so that when we can refer to it, you'll know which theorem I'm talking about. Nobody else in the planet's going to call it Theorem 6 except us. Okay, so so we still have the same setup. We have this vector field, and we're going to call the component functions P and Q. If that's a vector field on a region D, well, what we need are all these conditions: continuous partials, blah, 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 cross partials equal, and one more piece. Okay, so if this is true, where three conditions. First of all, whatever D is simply connected. And second of all, P and Q have continuous partials. Same condition as above. And three, these cross partials are equal everywhere in D. Then that's enough. This is the extra bit of information that we have to add in order to have this no answer turn to a yes answer. Okay. A lot of you may feel confused about this simply connectedness. I don't blame you. This is new. One of the big questions you're going to have is, how do you find D? I get all that. I don't want to get too deep into this because we could spend quite a long time on it. And so I'm going to ask not very deep questions about it, just because we're short on time. But these are all valid questions. I totally get it. And so let me just say, in practice, try, in practice, you have to come up with your own D. A lot of the times you may have to come up with your own D. And try D being all of the plane. That's simply connected. Or try D equals unit disk. That's simply connected. Really what you want to do is look at P and Q and decide for yourself where are look at the partial derivatives and say, are there any places where they're discontinuous? If there are, avoid that region. If they're continuous everywhere, you don't care, just make D be all of R2. If there's a place where they're discontinuous, then choose a D away from where stuff goes wrong. Away from any discontinuities of the partials of P and Q. Okay, so what this means is that, just to sort of follow up on what Joseph was saying a little bit earlier, if there are examples of vector fields which are have their component functions have continuous partial derivatives everywhere in some in regions that are not simply connected, and the cross partials are equal, but there's no simply connected region where that's true. And since so what that means, I don't know how to describe it. And so where there's no unifying potential function that produces f. Because of this sort of, you can go around a hole and maybe not match up where you started. That's sort of what goes wrong. Okay, so that's already too much to say about theorem 6. But let's talk about using it just in some sort of quick example. So you can see you don't really have to panic about D too much in the examples that I'm going to give you. Let's say determine whether the vector field f of x, y equals e to the y, x e to the y is conservative. We have a lot of ways we can do that. What are some options? I mean, I said using theorem 6, so I guess theorem 6 is an option. Could we use the equivalence theorem?
Yes.
Well, let's think about the equivalence theorem. Let me scroll back to it. Here's the equivalence theorem. See, the equivalence theorem, how would we show that it was conservative? We would have to show that for every simple closed curve, the line integral was 0. So we'd have to do a line integral for every single simple closed curve. That might take a long time, or like never. Or we have to do every pair of oriented curves starting at every point and ending at every possible point. Those would work.
If there are multiple ways of doing it, does it matter which one we choose?
No, but it could be that one way is easier for one vector field and another way is easier for another vector field. So I'm just talking about what your tools are available to you. This part is probably the easiest. See if you can find a potential function. That's going to answer the question right away. So if we do that direction, so way number 1, try to find a potential function. Oh, sorry, I already told you it was conservative rather than say determine. I'm sorry if I confused things. Try to find a potential function. So let's see, you would need a little f so that f sub x is e to the y and f sub y equals x e to the y. Well, in this case, little f would be x e to the y plus any function of y. And in this case, f would be x e to the y plus any function of x. And hey, there is a potential function then. Okay, so that's one way to do it. I just want to illustrate theorem 6. So here's way number 2. Way number 2 using theorem 6. So here's our vector field. I'm going to scroll up, so I'm just going to rewrite it here. Let's see, I can't have theorem 6 on the page at the same time, darn. Okay, so what do I need? I need a simply connected region. I need P and Q having continuous partials. I need the cross partials equal. So let's, we don't really know what D is yet until we get into all these cross partials. So let's say let P be the first component function and Q be the second component function. Then we're going to take all the partial derivatives. Then P sub x is 0. P sub y is e to the y. Q sub x is e to the y. Q sub y is x e to the y. Where are those continuous?
Everywhere.
Everywhere. That's right. All these partials are continuous everywhere. So everywhere in R2. Where are the cross partials equal? Where is P sub y equal to Q sub x? everywhere, right? So also, oops. So we'll just let D be R2. That's a simply connected region. There's no holes in it.
Oh, so when you say that we would like practice it ourselves, we just create like some possibly conservative function and then determine it like this?
Yeah, right. There's one homework assignment that says use theorem 6 to decide whether it's conservative, just as a little practice. And you don't have to get too weird about D. There'll be some obvious choices for D that you can use it for. Okay, so then by theorem 6, F is conservative. Okay, that's all I have for today. Tomorrow, we're going to talk about Green's theorem, which is just unbelievably cool, and it's going to save you a lot of time. It's going to be another shortcut for doing line integrals, and it's going to be another version of the fundamental theorem of calculus. So what's not to like? Okay, so who has questions? I think we still have like 3 minutes if anyone has a question.
I just have a question about the like the I don't know how to say it. Like guess the grading for the rest of the semester. So we have this exam, and then we have the final, and then we have the homeworks in between. Is that the only things that are left contributing to our grade? I just want to make sure we don't have another exam in there.
Nope.
Okay.
Same as the original syllabus.
Okay.
Yeah.
Thank you.
Any other questions? Okay, nice to see everybody. I look forward to seeing you tomorrow. Oh, you have a question?
Sorry, I have one more quick question. If you were to scroll up where you were talking about in practice, you can come up with your own region.
Yeah.
I just wanted to see what the last part said, if you don't mind.
Oh yeah, discontinuities.
Yeah,
This is
I'm gonna
really hard to read.
take a picture real quick.
And do you know that I post them all on Google Drive, right?
Oh yeah, that's right. I'm sorry about that.
You can, no, sorry. But yeah, you can watch the lecture again if you didn't understand something that I said, or you can download these files and stuff.
Okay, perfect. Thank you, Professor.
Sure. Okay, see you guys tomorrow.
13.3 tomorrow, right?
Oh yes, thank you for saying that. I'm sorry I didn't, but yes, please, 13.3 due tomorrow. Yeah.
Okay.
Okay, cool. I'll see you.